Okay, so good afternoon, everyone. Modeling and simulation of geophysical flows. So what we wanted to propose to do here, so let me talk about who we is. So there's me, I'm in the Engineering, Science, and Mechanics department. My main collaborator is Tryon Iliescu, he's in the Math department. And then we have Omer, who when we get to the publications, the page, the quad sheet, you'll see his name quite a bit. Omer was my PhD student in ESM, and now he's doing a postdoc with Tryon over in the Math department. We have Eric, who was Tryon's PhD student in Math. He's just graduating. He's defending in a couple of weeks, and he's on the market. And then we have Layla, who is my student in ESM. She's getting ready to graduate in 2014, 2015. So the main question is, can we apply new emerging classes of multiscale methods to the standard geophysical fluid dynamics problems to any benefit? So there are these emerging classes of multiscale methods, the equation-free framework put forward by Kavrakidis at Princeton, the heterogeneous multiscale method put forward by Wine and E, who's at Texas now, I believe. He was at Princeton as well. And why do we think that they would be useful? Well, geophysical fluid dynamics flows vary from a huge range of time scales and length scales that you can see in the problems. If you look at the smallest variations, they're on the length scales of centimeters. In weather, for example, if you look at the largest variations, you've got El Nino oscillations that are the scale of the Pacific Ocean, right? And then the time scales, you can have weather events. You see in Blacksburg it's snowing this morning, or it was snowing this morning, not this afternoon. And then when we get into really long time integration of these equations, we're talking about climate, right? So lots of really effective, successful, reduced order GFD models were developed in the 20th century, but if we want to integrate them for long times, we've got to take relatively low resolutions. So our objective and our approach was to develop a numerical laboratory of several GFD models. So here on the bottom left here, we've got our hierarchy of GFD models. So starting from the simplest way to represent a three-dimensional geophysical flow, the quasi-geostrophic equations, increasing in complexity with the shallow water equations, increasing more with the privative equations, which are basically the Navier-Stokes equations, the incompressible Navier-Stokes equations, and then moving on to the Boussinesq equations, where we start to include compressibility. So easiest to compute to hardest to compute. And so the idea is develop this numerical laboratory of all of these models of increasing difficulty and then apply a suite of modern multiscale approaches and see if there's any benefit to them. And so the multiscale approaches we had in mind when we started, and I'm going to try to find a mouse or there. Okay, this is better. So the multiscale approaches we had in mind when we started were the equation-free method from Kavrakidis. Truth be told, we tried really a lot to get some sort of approach that worked with the equation-free method, and we didn't really get anything that worked out using equation-free. It's a way to, how should we say, it's a way to simulate a system in time when you don't have an equation in closed form for that system, right? And so we tried again and again to do this with the global variables in different systems, and it just hasn't worked out for us so far. We looked a little bit at proper orthogonal decomposition. Omer is actually working with Tryon on this now. But the areas where we had our biggest success were in large eddy simulation, were in new closure strategies, and in domain decomposition. So I just wanted to highlight on the technical highlights page 2 of our biggest successes. So we've come up with a new closure strategy for large eddy simulation that's really suited to geophysical flows. So all the closure strategies for large eddy simulation in the past have been taken from three-dimensional turbulent flows. And the physics of these flows is fundamentally different. So in engineering flows and fully three-dimensional turbulent flows, you have an energy cascade that's going from large scales to small scales. Right? In geophysical flows, the flows are stratified and they're approximately two-dimensional. You actually have an energy cascade in the opposite direction. So all of these closure models, or most of them, were based on phenomenological modeling with this idea of a forward energy cascade that's totally inappropriate for geophysical flows. So we proposed using something called approximate deconvolution, which is a purely mathematical approach to the closing this problem. So just a quick recap of large eddy simulation for those of you who aren't familiar with it. Instead of simulating all the scales in a turbulent flow, you truncate at some intermediate wavelength. You don't simulate the small scales, you model them, and it saves lots of computational time, right? So in engineering flows, which are mostly three-dimensional, there have been lots of successful modelings of the small scales. In geophysical flows, it's been problematic. So we proposed this approach, which is totally mathematical, it's not phenomenological, and we've had a lot of success with it. In fact, we had, I didn't want to write this on measures of success, but one of the leading people who's modeling ocean flows for climate got in touch with me and with Omer a couple weeks ago and came and had lunch. So there's a lot of this approach has generated a lot of interest. So here we can see this is an ocean basin flow, so large-scale ocean circulation. And we've got the direct numerical simulation, so the full simulation results on the left, and we see 4 gyres, or vortices. In the middle, we've got LES, so where we truncate, we only simulate the large modes, but we've got it with a different closure modeling that's not as good. And then we've got it on the right with the approximate deconvolution approach, and it captures the right behavior. In fact, there are 4 gyres here, and if you use a different type of closure approach that's not appropriate for geophysical flows, you get the wrong behavior, you get 2 gyres here instead of 4. This is the stream function that I'm showing. Another technique that we had a lot of success with was domain decomposition. So the basic idea here is a lot of these fluid dynamics equations, you're solving an elliptic subproblem, you're solving a Laplace equation to meet some condition at each time step. Well, it turns out we discovered that if you solve this on a different grid, you can actually lower the resolution of the grid on which you solve the elliptic subproblem with no cost to the accuracy of the fine mesh flow field, right? And you can actually reduce the second grid accuracy quite a bit. So I've got different resolutions here. This is a 3-dimensional turbulent flow. It's Taylor-Green vortex flow. And I've got vorticity, the x component of vorticity at a certain time and a Reynolds number of 200. And this is the DNS in the top left corner. So this is the exact result, what it should be. And then it's probably too small to see, and I'm sorry, I really tried to get everything to fit onto these 3 slides with the font sizes that were given. But if you can see up in the upper left corner, it says 512 or 256 cubed colon 256 cubed. So that means that both the velocity field and the pressure are solved on the same fine resolution. And as we progress to the right and come down to the bottom and progress to the right, what's happening is we're solving the pressure field on a coarser and coarser grid. And there's a little bit of a difference. So the top row is both pressure and velocity on 256 cubed, and then we go to the middle, velocity still on 256 cubed, and we've got 128 cubed for pressure. Here we've got 256 cubed for velocity and 64 cubed for pressure, and it looks just as good. And if you look at the numbers, if you look at the error estimates, they're the same order of magnitude as this calculation. It's amazing. If you look at the bottom row, however, this is a little bit different. This is changing the resolution of both fields. So here we've got 128 cubed and 128 cubed. Here we've got 128 cubed and 64 cubed, and here we've got 64 cubed and 64 cubed, and you can see that there's just a lot of error that comes into the calculation at this point. It's under-resolved, right? So we've had success applying this to just general turbulent flows in 3 dimensions, homogeneous and inhomogeneous. We've got a Journal of Computational Physics paper from this. As well as applying it to these ocean circulation models. We've got a paper in Journal of Multiscale Engineering based on applying this domain decomposition to oceanic flows. So future directions, well, what we're really excited about, Tryon and Omer, they're not on this grant anymore, but they're looking at POD, proper orthogonal decomposition, applied to these geophysical flows. What I'm really excited about personally is applying this 80 approximate deconvolution closure to LES of atmospheric flows. So we've looked at oceanic flows. There's a whole different set of issues in atmospheric flows, and I'd love to see if it works there just as well. And also to go back down our hierarchy of GFD models and try applying it to some more complicated models for geophysical flows. Sponsored research, well, thinking about NSF Inspire or maybe an interdisciplinary NSF grant. I did apply to NSF Fluid Dynamics for similar topics, and it wasn't really the right program to apply to. I've looked around at NOAA a lot. NSF used to have a collaborations in mathematical geosciences program that they no longer have. It would have been perfect. So I've had a little bit of a tough time finding the right program to apply to for these types of ideas. So quad sheet, these basic accomplishments, so this new closure for LES and the flows we've applied it to, and then this new coarse grid projection domain decomposition method and the flows we've applied it to. So 2 ocean modeling papers, 2 computers and fluids paper. This first computers and fluids paper was the most downloaded paper for over 3 months on the computers and fluids website. 1 Journal of Computational Physics paper, which is in my field considered a very good journal. 1 to appear in Journal of Computational Multiscale Engineering, 1 in Computer Methods and Applied Mechanical Engineering, I believe. That's the name of the journal, and 1 under review in International Journal of Numerical Methods and Fluids. Key collaborators, Zhu Wang was a PhD in the math department here. He's at the University of Minnesota now doing a postdoc, and David Wells in the math department.